at the top of the hour. Hello, my name is Kathleen Stanton, Associate Vice President of Technical and International Affairs at the American Cleaning Institute. And I welcome you to our webinar today, Handle with Care, Methods for Measuring 1,4-Dioxane Concentrations in Cleaning Products. This event is in collaboration with the American Cleaning Institute. We will be reviewing the assessment of methodologies to measure 1,4-dioxane, and then we will have a panel discussion. Please put any questions you may have into the Q&A section of your control panel. All registrants will have access to the webinar recording, and attendees of the live broadcast will receive a certificate of attendance. Our article, Precise Measurement of 1,4-Dioxane Concentration in Cleaning Products, a review of the current state of the art, was published in the November 2022 issue of the AOCS Journal of Surfactants and Detergents. 1,4-dioxane is classified as a potential human carcinogen, and New York State passed laws limiting its concentration in daily use products. California is considering similar laws. Our panel are the contributing authors of this article. Brittany Hubert is a research scientist at Indorama Ventures Integrated Oxides and Derivatives, where she works as a primary analytical scientist, chemical hygiene officer, and team member. Brittany earned a bachelor's in science and chemistry from Nicholls State University and a PhD from Louisiana State University. Mike Williams received his master's in science in organic chemistry. Upon graduation, he worked in the pharma industry doing process development and scale-up. In 1998, Mike became a production chemist for Toma Products. Since then, he has been a synthetic research chemist, group leader, and senior group leader. Mike's groups are responsible for new products, process development, analytical research, and method development, and new product introductions for 4 of Evonik's Care Solution America's facilities. After several corporate name changes, Mike still sits at the same desk, but he works for the Evonik Corporation, where he is the Milton R&D manager. Nathan Pahacek is a director of product safety and stewardship at Ecolab, where he is a toxicologist as well as a staff manager. In addition to this work, Nathan is a visiting lecturer at the University of Minnesota and an active contributor to the American Cleaning Institute. Prior to joining Ecolab, Nathan had experience as a toxicologist in academic, regulatory, and industrial settings. Nathan earned a bachelor's in science and environmental science and ecology from Minnesota State University and master's in science in toxicology and microbiology and an MBA. He's a diplomat of the American Board of Toxicology and is active in multiple professional societies related to toxicology and adjacent disciplines. He is a Charles E. Wharton Institute Professor of Biosystems Engineering at the University of Tennessee. He received his Bachelor of Science at Iowa State University and his PhD from the University of Michigan, both degrees in chemical engineering. He also earned an executive MBA strategic leadership degree from UT in 2022. He served as a postdoctoral research scientist for the U.S. Department of Agriculture from 1991 to 93, and then a professor of chemical engineering at the University of Alabama from 1994 to 2003, before joining University of Tennessee in 2004. He is also an adjunct professor of chemical and biomolecular engineering, an Oak Ridge National Laboratory joint faculty member, and a guest professor at Jinyang University in China. He currently serves as editor-in-chief of Journal of Surfactants and Detergents and is on the editorial board for 3 other journals. He has received several awards, including being named Fellow of the American Oil Chemists Society. He has co-authored over 100 journal articles, 23 book chapters, and co-edited 3 books. His research interests include surfactant self-assembly systems, biodegradable plastics, environmental impacts of nanoplastics, and enzymatic reactions in non-aqueous media. With that, I will hand things over to Doug for the presentation.
Thank you for the very kind introduction, Kathy. Let's go ahead and get started. So again, here's the authorship. These slides will be made available to you all through AOCS. Here's the paper that Kathy referred to. This has much more depth in the details than what I will present today. And I'll basically, my presentation will be an overview of what's in this article. And I would be remiss if I did not, as editor-in-chief, invite you to submit your manuscripts to Journal of Surfactants and Detergents. We would look forward to receiving them. Executive summary, up front, what we're going to be showing you. 1,4-dioxane, I'll abbreviate that as 1,4-D, is a minor byproduct that comes out of the preparation of ethoxylate surfactants, especially sodium lauryl ethyl sulfate, SLES. And as Kathy mentioned, it's a persistent pollutant that is a potential carcinogen, and it resides in lakes, rivers, and groundwater. It does not break down very quickly, so it's in the environment for a long time. As a result, the state of New York enacted laws that took effect in January of this year that limited the amount of 1,4-dioxane that is allowable in personal care and cosmetic products. So the current law is that at most a commercial product can have 2 parts per million, and that'll go down to 1 part per million in early 2024, and then cosmetics products less than 10 parts per million. What I will show you is the best way to meet this great challenge of measuring 1,4-dioxane so precisely is to use GC mass spec equipped with either a headspace or solid phase micro extraction sampling environment. Here is the website from the state of New York highlighting these changes, these laws that were enacted here that I just discussed on the previous slide. As Kathy mentioned, the state of California is considering similar laws. Australia is also taking into consideration making laws, as is Germany and other countries in the European Union. A little bit about 1,4-D. As mentioned, it's a potential carcinogen to humans, even at the small concentrations that would be encountered in drinking water, parts per million or smaller. In neat form, it also is a irritant. The problem with 1,4-dioxane is it does not break down in the environment. It has very limited biodegradability. In neat form, it's a clear flammable liquid. It has a molecular weight about 88 grams per mole, and its specific gravity is very close to that of water, 1.03. The melting point is 11.8 degrees C. The boiling point very close to that of water, just slightly over it at 101.1 degrees. If one was considering trying to remove 1,4-dioxane from water, a hindrance would be the presence of an azeotrope, which occurs at a mass fraction of 1,4-D of about 0.821 and a temperature of 87.6 degrees. This cartoon shows where 1,4-dioxane occurs, and specifically we're looking at the formation of SLES, or again, sodium lauryl ether sulfate. The starting materials are fatty alcohols and ethylene oxide, which through the ethoxylation process will give us this fatty alcohol ethoxylate. It turns out that we can also form 1,4-dioxane during this process, or even directly from ethylene oxide, but this is not the primary route for its formation. To make SLES, we will react a fatty alcohol ethoxylate with sulfur trioxide or an equivalent sulfur donor, and we will wind up getting the sulfate. And the sulfate group is catalytic and helps drive the formation of the 1,4-dioxane ring. And then our fatty alcohol ethoxylate will come out also, but it'll have 2 ethoxylate units less in its degree of polymerization. So the problem we really have here is measuring a needle in a haystack. It's a great challenge to be measuring at such, again, such low concentrations. We also have, well, let me point out something. There's been a fair amount of literature work of people trying to measure 1,4-dioxane in drinking water, groundwater, and other environmental matrices. And that has occurred fairly reasonably accurately. The problem is when we start looking at measuring 1,4-dioxane in personal care and cosmetic products, now we have a lot of other components that could be in there that could really affect our signal to noise ratio in the analysis. So what we have to do is not only have good analysis, but we have to also simultaneously isolate and concentrate 1,4-dioxane from that matrix, since we're at such small concentrations. These are some typical run conditions for capillary gas chromatography. This comes out of not only in the environmental matrix data and literature, but also out of recent literature involving commercial products. Typically, a nonpolar column is used that is rich in PDMS. There's a temperature programming that's occurring, ramping up to roughly 200 degrees C. Both split and splitless injection have been used. Carrier gas, just a common inert gas such as N2 or helium. The preferred and more accurate measurement of the detection is mass spec, specifically in selected ionization mode, or SIM, which I'll talk about in the next slide. It's also really important for the quantification at sub ppm levels that we have an internal standard present. The most robust internal standard is per deuterated 1,4-dioxane, or 1,4-D dash lowercase d8. A typical sample preparation is to dissolve in water or a solvent, or in some cases, just to use the sample itself. This is some analysis work where the authors injected 1,4-dioxane, 1,3-dioxane, and then the per deuterated 1,4-D in the same sample, and then they analyzed each individually using MS and the SIM. You can see here's the total ion count at the upper left. And then we have specific channels for our 1,4-D that would be using a mass to charge ratio, or MZ, of 88. And then for 1,4-D8, it's 96. And then if 1,3-D, it's 87. And we can see clearly that these peaks do resolve from each other. We can do a separation by chromatography fairly well. And then here are the mass spectra. Here is the 1,4-dioxane. Again, its major peak is for the molecular weight, which is 88. And then also there's a peak occurring at 58. And then for 1,4-D8, per deuterated, it's at 96 with another ion at 64. So what we're going to do now is talk about that challenge of how do we isolate 1,4-dioxane from our sample so that we have enough injected onto the column to see it. Here are a couple of ex situ methods that are well known. One is liquid-liquid extraction, another solid phase extraction. and then azeotropic distillation can also be used. For LLE, a common way to do this is to take a chlorinated or nonpolar solvent, dichloromethane, for instance, and then we have a liquid-liquid separation, and our 1,4-dioxane will be enriched in that dichloromethane phase. For solid phase extraction, we essentially load our sample onto a column, and then we look at different eluents. We have a wash eluent that will wash away the contaminants, and then finally we'll have conditions and a solvent that'll selectively remove our analyte of interest. So it comes out in a concentrated form with very minimal amount of interfering analytes present. So some advantages and disadvantages of this ex situ approach. The instrumentation and supplies are inexpensive, and the samples are very clean and ready to go for injection into the chromatograph. Some disadvantages: the selectivity is moderate. There are other methods that will give us better selectivity toward 1,4-D. It requires large volumes of sample as well as organic solvents. So cost is going to be an issue, and also environmental sustainability. It's also quite laborious and time consuming. More recently, the approaches that have been used for GC mass spec analysis of 1,4-D are these methods that are in situ sample preparation. We have purge and trap, or PT, headspace, or HS, and then solid phase micro extraction, or SPME. In the next 3 slides, I will discuss what each one of these 3 represents, how it works, and then we'll look at some very specific data involving the latter 2 coming up. So here's purge and trap, or PT, and it works like this. We have our sample, and we're going to put our carrier gas through it, and that carrier gas is going to carry our analyte of interest. Of course, we will control our conditions here in the sample cell so that our analyte of interest, 1,4-D, is going to selectively partition into the headspace. That would be things like increasing temperature or decreasing pressure. And then they will adsorb onto this trap. And of course, this will be done with not any connection to the column. And then when we're ready for our run, we will incorporate conditions that will release 1,4-dioxane from the adsorbent trap. So it'll go directly in a concentrated form into the column. Here's the second example of headspace sampling. The idea here is that we will again control the sample conditions so that our 1,4-dioxane is going to partition strongly to this headspace. And we will control the solenoid valve so that we can inject that headspace into the column. And then when we're done, return the solenoid valve back to the carrier gas to continue the analysis. So these are some things in our toolbox that we can use to increase the partitioning of 1,4-D into the headspace. We, again, temperature and pressure, we can control the volume fraction of the sample in the headspace, the equilibration time, as well as the salinity. If we add salt if we're doing this in water and we add salt, that will drive the partitioning of 1,4-D into the headspace. This is some examples of that. The Fernando study, which we're going to talk about in a couple minutes. And what they did is try to optimize the headspace sampling through temperature and also incubation time. And the temperature was optimized near the boiling point of 100 degrees for 1,4-D. And then the incubation time, 10 minutes proved to be pretty reasonable. 15 minutes gave us maybe a slight improvement, but to save time and efficiency, 10 minutes is fine. And then the third in situ approach involves SPME, or again, solid phase micro extraction. The idea here is that we're going to incorporate a microfiber into this tightly sealed, specifically designed sample vial. We will again control the conditions of the vial, temperature, salinity, and so forth, to drive 1,4-dioxane into the headspace. But in addition to that, we will have adsorption onto that fiber, so that we'll have an even more concentrated and selective adsorption of 1,4-D onto that microfiber. And then that microfiber will be desorbed and go directly into the column. And we will use conditions for desorption so that the release of 1,4-D will occur. Another approach to improve the signal to noise is, instead of using MS, is to use tandem MS, or MS/MS, using a quadrupole system. And this is a way to address the interferences that might come from other matrix components. Even in selective ionization mode, there sometimes are other peaks that form. And the idea here is that we will do typical mass spec ionization. We will use our SIM and look at the 88 or 96 MZ, and then we'll hit that stream with photons and break into fragments. And we will measure the fragments that come out of this. And specifically with 1,4-D, we get fragments that occur at 57 to 58. And then for the produterated, it occurs at 62 or 64. It does give us a reduced signal compared to the just standard MS. But again, it is good for reducing the impact of interfering compounds that may be in the matrix. The last part of my presentation, we're going to look at two studies that were recently published. The first is from Fernando et al. In Clarkson University, upstate New York, and they used headspace GC mass spec. And then the second study is coming out of the Cal EPA, specifically the DTSC, or Department of Toxic Substances and Control, and they used SPME and also tandem MS. So looking at the first study from Fernando, here is a schematic of the sampler that was used for the headspace analysis, which again was connected directly to the column. This was again a dedicated apparatus that came with that they had to purchase, and then there's a transfer line. Here are some conditions that need to be optimized for this sampling environment. And one of the key ones is the transfer line and getting that temperature right. And 120 degrees was correct for them. This is a series of all the conditions that they used for analysis. And you can see here the oven programming, the carrier gas, so on and so forth. And then here are the MS parameters over here. And again, they used 1,4-dioxane D8 as the standard. They had some outstanding chromatography work. Their limit of quantification, or LOQ, was 1.3 parts per billion, which provides the necessary precision to measure to meet the requirements of the state of New York. And the standard deviation is about 5.1%, which is a good repeatability performance. And then what Fernando et al. Did is they had a series of samples, cleaning products here that they looked at, and then I'll show you in a minute some personal care products. And all of these samples were also measured by the second method from Cal EPA. This is just the results from the Fernando group. The color legend here is if it's green, these products, you can see the number of products here in the legend, are compliant with the New York state law. If it's yellow, it's compliant with the 2023 state law. It has to be at most 2 parts per million. And then the red is ones that will not be compliant. I have that wrong, actually. The yellow is currently compliant by New York and will not be compliant in 2024. And the red is not compliant right now. We can see here that most of the products are compliant with the exception of manual dish detergents and also laundry detergents that were tested. Here are personal care products, and here we have the same legend. We can see for all 3 products that several products, whether they be hair products, baby hygiene products, or body cleansing products, do not meet the requirements of the state of New York. This is cosmetic products that were tested, and in all cases, the products were compliant with the 10 part per million criterion that the state of New York legislated. We'll now move on to the second method, which is looking at, again, solid phase micro extraction with the tandem mass spec. And this, again, was developed at the Cal EPA. Here are the oven conditions for the GC, as well as the mass spec conditions. And I'll just, again, I won't dwell on those to save time for discussion. One of the things that the authors did is they looked at different matrices for SPME, and they found that this CARB PDMS matrix performed the best. It had a good recovery, good peak shape, and this is the one that they used in their subsequent studies. And then they also looked at incubation time and temperature conditions to recover 1,4-dioxane. Note they also looked at salinity, 10% sodium chloride or no sodium chloride. The best conditions here in purple are at 70 degrees C using sodium chloride. This is some of their analysis data looking at spiked samples just to see how well how linear the response was and how low in concentration it can measure. You can see this is a very impressive linearity, and they were able to have an LOQ to 0.037 parts per billion. That's very impressive, and a very good RSD of 3.7%. And their finding was just having the 1,4-dioxane D8 was very, very important for quantification to correct for any interferences that may occur due to other matrix components. And these are some best practices that they published in their literature about how often one needs to redo the calibration standards, do matrix blanks to make sure there's no carryover and things like that. So again, a lot of good information there on best practices. So to kind of wrap up here, we're going to look at some advantages and disadvantages of these 2 methods. Both are very effective methods to do analysis of 1,4-D of personal care products. Some of the advantages of the headspace analysis: low solvent volumes and small sample size, and the sample preparation is very quick. The disadvantages would be the instrumentation that would be needed, which is specialized, and also maybe longer time for the sample to undergo preparation before injection into the column. The SPME advantages are it's rapid, very low amount of labor, and no solvent involved at all. Disadvantages, we can have column bleed occurring and or carryover between runs. So conclusions, both methods, the Headspace and SPME, were effective for analysis of 1,4-D at the ppb to ppm level. Using a robust standard is essential, and the per deuterated 1,4-dioxane again is the best way to go. Tandem mass spec is effective in reducing the impact that may occur from interfering components in the sample matrix. These methods, both of them, are effective to address the new laws enacted by the state of New York and the other laws that are likely to occur in other states and other countries throughout the world. Just some recommendations that we have. More work is needed to understand the interferences, and this will occur as the set of samples being analyzed for personal care or home care products expands. A cost analysis is also very important to be doing with these two methods for the long term, since each batch of product sold in New York would have to be examined. Another recommendation or reminder, not only does one have to very carefully do the chromatography, but also in making that sample and having a very accurate mass sample, for instance, if you're adding that personal care product to water and doing that very accurately, there needs to be new approaches that continue to be developed. One that is promising is single drop micro extraction, and then things like pulse split injection that can be used. On a broader perspective for the industry, the personal care and home care industry, improved manufacturing needs to be continued. A lot of progress has occurred in the 21st century to reduce the amount of 1,4-D produced by having more efficient and selective catalysts. The storage of 1,4-D and other ethoxylated surfactants also has to be better examined and evaluated. The other approach here to address this problem is to reformulate so that the amount of SLES in the product is less or it's eliminated. There has been progress over the last 20, 30 years in developing tools such as the HLD model or hydrophilic lipophilic difference model to help the formulation process to be more efficient and less time consuming. With that, I will just show you our references, and I greatly thank you for your attention. These are all the affiliations of our authorship, and I'll turn it back over to Kathy.
All right, thanks so much, Doug, for that presentation. I just want to let everyone know that unfortunately Nathan will not be able to join us, but we will now transition into our panel discussion and reintroduce our participants, Brittany, Mike, Doug, and myself. Again, if you do have any questions, please don't hesitate to put your questions in the Q&A box. We do have a few that are sitting over there. So the first one isn't so much a question, but a little bit of a thought is, I'm not sure that it comes from cosmetics, having worked in petrochemicals. I do think cosmetics aren't the biggest culprit in this equation. And I can say that, yes, in the past, it was unintended spills, historical disposal practices, and industrial wastewaters have been identified as the major sources of 1,4-dioxane. What we're dealing with in this time is the unintended introduction of a contaminant into products, whereas they're now being regulated by states and perhaps beyond states, looking at the international scene. So with that, the next question is another observation, having to do, seeing that HGGC with FID gives sufficient sensitivity without requiring a mass spec. So is there any response to that, or is that something that we usually can see?
Well, I'll start out the discussion, I guess, and just say, you know, again, if you have an environmental sample, maybe it's an aqueous sample that's relatively clean, I think FID would be fine. I think it depends on the level of precision that you need to get. But particularly for home care, personal care products, there's so many different compounds in there that can interfere. Having the mass spec and operating in selective ionization mode is extremely important to get that, to isolate that compound chromatographically.
I gotta agree with Doug on that, because with FID, it's just so matrix dependent that you could run into so many issues. Going to a mass spec really helps with that, because you can get down to really low detection levels in a pure matrix. But anytime you introduce those other compounds, it's an issue. So.
And another question related to FID is, can FID be used to detect 1,4-dioxane and HE and SPME techniques? And how much do you think the LOQ would be using it?
Brittany, what are your thoughts?
For FID, probably the best that we've gotten is about 0.5 ppm, and that is very specific to the product. So like we've already said, it's very specific to the matrix. Again, this is why we definitely suggest mass spec, is because we can get a better chromatogram with that and better separation with the spectra for mass spec.
Great, thank you. We have a question. First, Doug, thank you for the presentation and congrats on the paper. Nowadays, there are several surfactant production companies that indicate they are producing quoted ultra-low 1,4-dioxane surfactants. Would you say they use this technique to measure their ultra-low content? Are there standardized methods for part per billion, part per million values?
And I'm going to open this up to the panel. I'm not aware of any, first of all, on standards. That's not there yet, although I think that's a good idea. In terms of what's going on in the industry, I will defer to my co-authors.
Actually, Doug, I'm going to point out the way I read the question, are there standardized methods? The paper that we put out is the standardized method for measuring that low, the ppm and ppb levels. That's the way I read Ron's question, at least. And yeah, it is I would say that the method does achieve the ultra low content, because with the headspace method, you can get down to 50 ppb as your LOD, and you get down to 10 ppb as an LOD with a SPME mass spec. So I call that ultra low.
So there's a question of, can you expand on sample preparation and selectivity? I don't think this is just related to the one product category that they're talking about. I think that's like, what is the sample preparation and selectivity for all the samples?
I can speak on the headspace sample prep. And for this, it's very simple. You can do 2 grams of sample and 2 grams of 1 ppm or 2 ppm deuterated dioxane. So this is very simple sample prep, and I'll let somebody else speak on the SPME.
SPME is similarly easy. I mean, very similar quantities, and literally you take your final formulation, drop it in the vial and run it. So it's super simple sample prep. With the coatings though, I haven't never tried any of our coatings products on a SPME-GC spec, so I can't speak to it directly.
So one of the questions we have, how do these and other methods compare on standard sample of known 1,4-dioxane concentrations in terms of what numbers they give?
Well, I think that's in progress. I mean, again, I think that's the idea that what I presented were some a set of samples from home care and personal care products, and I showed the results that were obtained at Clarkson University. The same thing's going on right now in California. So I think that's the idea, is to match, to see, compare the two performances, and that hasn't happened yet.
One of the questions says, the mass specs still require a matrix match calibration due to the ionization impacts?
Brittany, your thoughts? I'll let you go first.
I have not seen so much of this for matrix effects, but it does stand that it needs to be tested just to verify that that's not the case. But we have more of raw materials for Indorama than we do for cosmetics, her personal care formulations.
That's also where we stand, being on the supplier side also. Just most of our materials are, like I say, on the raw material side, so we don't see those matrix effects. You should always do a proper method validation though whenever you're trying a new method. So. Next. Kathy, you're muted.
That would help. There's a couple of questions related to the progress of evaluating the generation of 1,4-dioxide over time due to temperature, pH, etc.
That was the basis of that Stepan tech info note that they released a while back, and the increased 1,4-dioxane with storage conditions, but that was pretty specific to the sulfates. I know we haven't seen them on other products from a storage stability standpoint.
I agree. The same thing that we've observed too.
So that takes care of a couple of those questions. How do you test the repeatability and accuracy of both methods?
Well, the approach that's been used in both the Cal EPA and the Clarkson studies are basically involving spike samples and looking at the recovery, looking at the repeatability, concentration series to make sure that we have a linearity in the concentration versus detector signal relationship. Mostly pretty standard procedures for doing GC and analytical analysis.
So we have great presentation on the details of PCP analysis. Any comment on why the leading mass contributors, detergents and shampoos, have the lowest reliability?
Lowest reliability of what? I'm not sure I understand that question.
I think what they're trying to get at is almost, why did we have to come up with a new technique in order to measure these products, because we're using, things that weren't quite up to snuff, I would say, because it's such a complex matrices.
Well, if I may add too, that just the looking at the sample set that I presented on Clarkson, those were the samples that that had the highest number or fraction that failed the New York legislation.
Anytime there's new regulations with new limits, you're probably going to have to develop new methods just to be able to meet those. At least that's what I've seen historically. That would be why we have to keep abreast of what all these changes are. And that's also why we keep abreast of not just these changes, but other changes that are coming.
One question, are there currently published official methods for detecting 1,4-dioxane?
Not that I know of. Officially, no. And again, as Mike commented on, a standardized method is hopefully going to come someday, but we're not there yet.
I'd agree with that. There's not official methods either in the AOCS methods or ASTM methodology. So I would say that this is probably something that we'll be working on as an industry for a long time. As we know, standard making and publication, including validations, do take quite a while. So when we've been working on this, we were working with the intent to have something standardized, but what we're looking for in the short term, because we do have these regulations that have come into play, is to have standards that are usable for the purposes that we have in front of us. One question that we have, any thoughts to life cycle analysis? What do the results mean? Sensitivity of aquatic organisms to 1,4-dioxane is low, and the risk of human consumption decreases substantially due to dilution when wastewater is discharged to surface water rivers.
Life cycle analysis of any new product development that comes from any of the suppliers out there. So that's something that's commonly done, as opposed to interpreting what the results mean. You have to actually be looking at specific LCAs to be able to answer that part of the question, I believe.
I think that what this question is driving at is, knowing that the products were already low in 1,4-dioxane, when they go through wastewater treatment, and the effluent at the end of wastewater treatment, it's going to be very low 1,4-dioxane coming out at the end of that pipe as well. What do our results mean? I think a lot of this is currently being answered and assessed over at the United States Environmental Protection Agency, where they are doing a reanalysis of the risk assessment of 1,4-dioxane. And I believe that they are going to include surface waters and drinking water in their new assessment. So I think that this is something that we're a bit on a wait and see kind of situation.
Oh, Kathy, if I can add to that, I agree 100% with what you said. Another issue, and this was brought up by the Cal EPA, in California, the water cycle is some closed loop. So the water gets a lot of the water that gets used gets, again, processed and recycled, not so much released out to the environment. So if there's any 1,4-dioxane that gets entered into the watershed, it's usually there for a long time and it just accumulates. So that's one reason for the rationale of California pursuing legislation related to 1,4-D.
We have what has New York State said about the methods or standards it will use for enforcement? I think I can answer that and then you can chime in. We haven't seen what the regulation is yet in New York. They did put in the limits, but they are still working on what that regulation would look like. And from our understanding, New York State Department of Environmental Conservation will include something about their methods or the standards that they will use for determining the concentration of 1,4-dioxane in products. If no one else has anything to add to that. There is an ISO standard for 1,4-dioxane, but the MDL is high at 2 parts per million. So it's not fit for the uses that we have. Is there anything else? Some of the questions that are in here have been asked and answered in other parts. We do have a comment that pulse split injection does improve signal quality. There's a couple of questions and comments about the formation of 1,4-dioxane over time, which we answered before. So I don't see any new questions coming in, but thank you, Thomas. Yes, we're aware that the discharge scenario is driving the regs, and it's due to what's going on Long Island. Are there any special handling conditions when undertaking an accelerated storage stability study so 1,4-dioxane is not lost during storage or sampling?
I can answer. I think just making sure everything is capped very well. As soon as you open the container, you probably will lose dioxane. So just making sure you have a really good storage and tight seal should be fine.
With that, I believe that was our last question. There's no more open questions, but if you do want to submit a question, please do that very soon. All right. Any concerns or hopes from what you might see from EPA's reevaluation of the 1,4-dioxane evaluation? I think that for the American Cleaning Institute, when we sent and submitted our comments to EPA, some of the comments that we had were to look at these other, not just conditions of use, but other possible points of exposure. So we are happy that those are going to be included as well. I don't know if we have any concerns. What we hope, though, is to see that reevaluation soon. Don't see that we have any further questions. So we'll go ahead and thank everyone again for joining us. Please be reminded that you will have access to the webinar recording in the next day or two. And you will soon receive a certificate of attendance for attending our webinar. With that, have a great rest of your day and hope to hear from you soon.